Namaste all. Hope after a nice food, no one feel sleepy. Don't worry, I won't allow you to sleep because I won't explain anything about theory. Morning speakers, they have explained all the theory part and all. Just I will take you to some of the examples, case studies what we are exhibited and where ProSIM has bring their expertise in the field of fitness for service and remaining life assessment and asset integrity part. Okay. So as we all know, corrosion, we can't stop that one because it's a natural process and it can be predictable. We can avoid that one. So just moving to some of the examples, just I will take one vertical heat exchangers where I have shown the 2D sketch of the heat exchanger. You can see that because of the client confidentiality, I'm taking equivalent model of the work what we have executed. So with this the corrosion, when you are speaking the stress induced corrosion, so that it may be happen based on the based upon the local thinning or the effect of higher temperatures, or it may be fatigue the wall or units, whatever the load will happen, that is a cyclic loading. So based on this, it may be the stress induced corrosion it happen at the boundary condition and all. But if you see the real scenario in one of the oil and gas industry, when working with this vertical heat exchanger, if you see the physical picture, okay, it's already corroded at the exactly at the support ring part. So here if you seeing this picture, we can able to see there is the impact of the corrosion due to the on the properties, mechanical properties also, that comes material impact on material property, chemical properties and all. So here with the material properties, it will decrease the tensile strength and the ductility of the material. It will reduce cost for the crack initiation and the failure cause. Okay, with the chemical reaction and all, it will decrease the chemical stability and cause for the material degradation also. So this is where with this when there is the effect on the corrosion effect on the material, then they have captured we have captured the testing. So we have measured the all over the 360-degree found round part of the wherever the ring is supported. So we found the all 360-degree, it's a uneven corrosion has happened over all the things. So we have modeled the converting the physical image to the our modeling part. Okay, that is how you import it into empirical thing. So this is the measured data of overall 360-degree what you can you are seeing on the screen. So then we have converted that into our numerical method. So we have captured overall 360-degree. Just I am showing a part of that north to east. So with that they have a nominal thickness of 27 mm and each grid having a variance of thickness depth already. So we captured this in a grid levels overall the 360-degree. That will cause for the corrosion induced stresses. Okay, the corrosion induced stresses that will impact for the, because corrosion induced stresses, what will happen, the stress when there is a corrosion leading to a internal stress of a material, that will affect on the structural integrity part. Okay, that will cause, it may be impact on the structural integrity of like it may be a residual stress impacts, and it may be a failure of the fatigue failure, because the complete recycling of the fatigue failure, that will cause for the damage for the damage of the equipment. Okay, so by with the higher temperature and pressure operating condition, we have executed with the coupled thermal analysis where the material behavior has to be converted into all temperature gradient part and all. So we have defined with the temperature gradient, we can see the at the corroded region part what are the stresses over there, and comparing those stresses by taking stress classification lines, comparing with the allowables of membrane and membrane plus bending. So here we are suggested with the increase in the thickness at the west to north zone, because we have to take a quick call, because of the, if you leave the corrosion like that, it will definitely lead for catastrophic failure in the future. So by taking a quick call, maybe in the API and ASME codes, if you go through that, they will call for the level 3 assessment, detailed analysis of a finite element method. So using that method we have executed. Then moving to the next example, there is a heater tube oscillations. You can see that the 15 meter of heater tube, that there will be observing the oscillation, because in the frequency of operating conditions, the oscillation between this tubes are very high with displacement of 14 to 15 mm. Then we have studied on this So we have captured again for the material modeling. You can see the pin over that at the upper part of the tube, okay, where it is a connected happened at the outer tube and the inner tube, and the overall load by taking by the pin only. So if you see the physical image, that was not corroded because of again the contact between the tube pin and the tube. So there will be a calls for the boundary nonlinearity, okay. So capturing that material degradation and the boundary nonlinearity capturing, we have found out the what could be the contact stresses over there and comparing those stresses with respect to the allowables of the material. So next, coming to next case is a condensate tank. So this is just a equivalent model we have captured. Here what will happen, the condensation, it will taking all the excess of heat and the condensating from the boiler. So here the, if you see the stress induced by corrosion, they have a vacuum pressure inside and there will be a compressive load also from the heat exchanger. If you see the physical image of this, so exactly at the, there will be a ladder which is connected to the tank, exactly at the supporting location that was corroded. Again it's an unevenly, but this time that now it may be checked with elastic plastic, but how to degrading that material capturing the all the properties. We have checked for the load buckling factor, where we test the structure stability of the structure, where the up to what load the structure will takes place. So this is we have checked for the load proportional factor, buckling load factor, nonlinear buckling, where we have to tell what is the effect or what could be the thickness of over there. You can see in this finite element model where we captured the full corrosion thickness along at the blue line. So with the Riggs method, nonlinear buckling, we have found out what could be the thickness of this, where the structure will be unstable to sustain. This one. I'm moving to the next fourth example with the tank settlement. Here our objective is to inspect what could be the, because they had some of the corrosion issues during the inspection. They want to check with the, because of this structural stability or structural integrity of a tank, by seeing, by capturing with the testing and all. We have not taken part of the nozzle and all, because those corrosion it would be okay that by changing gasket and the bolt material and all. So you can see the, we have measured with the enhance of the technology with the UOT, we have captured the laser scanning. From the laser scanning using the cloud data, we have converted the cloud data model to a FE model. So this is the how the tank, you can see the annular plate at the base where it is not even to the flat to the foundation part, okay, because of the after commissioning of 10 years it was the settlement was, this was the text base. So we did the integrity of the tank, structural integrity, and found the results or be okay with the range of this. So this is for fourth example of the tank settlement. Now moving to the corroded pipe. Though for the offshore pipeline, you may think the it's a defected pipe. Inside there is a depth of a certain 6 to 8 mm of depth. We have done some iterations and all. Here both internal and external pressure were there. So the problem might looks like a very easy, but if you going deal with the corrosion with the, all the properties and all. So this corroded pipe with the defected size, we keep on increasing and studied the effect of that. That I am not showing here. Just what we did with the one of the defect size, we have undergone and studied, and that was we asked for the defected depth was not been okay within, not in the allowable stress of the membrane as per the allowable. So here if you see the behavior of the stress origin along the node path, both circumferential and on the longitudinal direction, how it looks varying with respect to the node distance, the what could be the stresses and all. So here you know the stress SCC, morning sir was explaining stress crack corrosion, okay. When there is a material sustained material and the environment that calls for the corrosion, when material and stress, or it may be a strain rate, that will call for the fatigue. When the strain rate stress will combine with the environment, it is a corrosion fatigue. When combination of degradation, it is called for stress corrosion crack, okay. So if you see the SCC in a pipeline, here it is not kept. We have checked for some of the circumferential welds where the SCC has been found out and the cracking has takes place. See, that is because of the combination of all the material degradation, and it may be a corrosive environmental and a strain rate of the defect. So similarly, SCC of the in a nuclear plants, if you see the example I am not showing here, the effect of high temperature components, because the nuclear plants are working with some of the plants working with higher temperature rate, because of the pressure and cyclic load of the temperature with the transient, that will cause for the SEC in the some of the component lead for the crack failure. And SEC in the nuclear fund, that effect of the radiation, the radiation effect impact, the impact of radiation on the metal, that accelerate the SEC, that again it cause for the failure of the material. Okay, so this I can say the finite element analysis, where you can predict the structural integrity, we can do and find the prediction of feasible points where it can be predict the corrosion, and we can take the call for what has to be done for the fitness of a service, or it may be change of the repair and all. So just concluding with the example, first one, in a heat exchanger, we have called for suggested to repair the west side portion of the strengthening the part of the heat exchanger. In the heater tube, we suggested with the tube guides to avoid the further oscillation. In the condensate receiver, we support a structure design with the modified for the safe operation. And fourth and fifth examples, tank and the corroded pipe, we have checked for the structural integrity part. That's all. Thank you.
Thank you very much for keeping your time, and there might be a question or two. Yes, please. How do you measure the shell thickness?
No, that is from the laser scanning the data, they have the thickness also. Yes. Yes. Abacus is the solver we use.
Okay, if there are no more questions, I'd like to, oh, you do have, sorry. Yeah.
What we basically show from your use cases all are in reactive in nature, like you just regenerated the stress extent plot when any corrosion has happened. So how do you like approach for finding out the predicted points before the corrosion happens? So can you just
that's what in the first example I shown, the prediction of the corrosion, it may cause at the thinning locally position, or it boundary condition, or it may be effect of the higher temperature, or and the loading. It's all, you take any type of loading, it's all in cyclic in nature. Okay, so with this it may takes place at the thinning portion or the boundary condition of the place.
So another follow-up, sorry sir.
Yeah.
I apologize. We have to, we want you to stay back.
Yeah, sure, sure.
And
I will talk to you.
there's going to be a tea break. I'm sure you'll have lots of time to interact if you don't mind. Yeah.